Okay, we're rolling live and ready to start with lecture 2. So we're done with the boot camp, and now we're going to look at, today we're going to look at data types and data abstraction. And this is lecture number 2, which is the first lecture really of the course after the boot camp. So this should be new stuff, maybe not. I talked about namespaces already, but I didn't talk about how to create them, stuff like that. Talked about built-in data types, literal constants, a little bit of mention on that. Variables, pointers. So this is not the entire pointer lecture, it's an overview of the pointer concepts. References, passed by value, passed by reference, C++ string types, and the constant qualifier. I'm actually going to get into structures and classes as well. This is going to be, it's like 100 and something slides. This is going to be a 2-part lecture. I'll start it today, and then we'll end it probably after next week or something like that. Unless I talk real fast and I'll do the whole thing today, but I don't think I'm going to get that far. So what is this using namespace std? We don't see this in Java. We don't have this problem in Java actually, but we do have it in C++. And in terms of the object-oriented component, it doesn't really apply. In terms of standard programming, it does apply. More of a C++ versus a C thing, because we're using a lot more libraries and we're doing a lot of high-level, I should say more complicated source code writing. But what we are seeing so far, especially if you download dev C++ and start using that compiler, Microsoft does the same thing, or the older versions did. They put this line in here that says using namespace std. std as a namespace is defined already. It's a std stands for standard, if you haven't figured that out. And the namespace concept, let's talk about that for a few minutes. The problem that this is trying to solve is that when you have two variables or functions, or anything for that matter, that's named in the global scope, you have the same identifier name, you're going to get a compiler error, even though you're referring to two separate libraries. Think of the concept of including a bunch of libraries, and when you do that, you might have duplicate names. And so what this does is creates the environment variables, environment spaces. And you create a namespace, you include libraries in it, and you use the namespace. std is a default namespace we don't have to create, we just use it, which is how this syntax came about. And what we're looking at is in blue on the slide, which says using namespace std, which comes right before main. After we said include IO stream, whether or not you have the .h there or not depends on your compiler. This is dev C++ code. And this should hopefully look familiar by now. We went over all this stuff last week. This is the boot camp stuff. So in terms of avoiding such name collisions, you need to use unique identifiers in your own code. So your own code is kind of predictable. You can actually write it yourself, so you are writing it yourself, so you can pick out your identifier names. But in C, if you have multiple third-party libraries, then there's going to be name collision. So you have 3 choices. You can get the source code to the libraries and modify and recompile it. Not such a good option, because you may not actually have all the compiler tools and everything you need for it. You can ask one of the library publishers to rename their identifiers. No, not such a good idea either. They're not going to change the name of their identifiers. Or you can decide not to use one of the libraries and only use one library instead of another library. None of these options are actually kind of available to you in most cases. It's better just to create a namespace. So the namespace was introduced to solve the problem. So all of the identifiers, and we'll see if you're not familiar with the concept of the identifier, it's the name that we're putting on the variable, on the namespace, on the memory space that we're naming. And so we can define them all in a block, associate the block with a namespace identifier, and we'll see an example of that in a few minutes. All references to the identifier from outside of the block must indicate the namespace identifier, which is why we say including. And we'll see an example. So one example is the namespace std. So we have the C++ is defined the default libraries such as cout, cin, iostream. All of that stuff is already predefined for you. And here we have, what if we didn't use it? So you can access the object in the namespace, and you can use the following, and this is kind of the introduction to the scope resolution operator. This is referring to a scope. When we say using namespace std, we're using the scope of the environment that is specified by the namespace that was created that we called STD or standard. That's built in. We don't have to create that. We could say STD, if we didn't put the including up here, this is a lot more work. So in the previous example, we looked at this here. We have this big old including up here. What if we just take it out? If we take it out, then we have to say, well, where is C out? Where is C in? And we do that by using the scope resolution operator. We're going to see this when we start looking at classes as soon as next week, actually. So here we have STD, and we have two semicolons that are back-to-back. C out, hello world, return 0 because we have integer here. So what we're doing here is we're saying inside of the scope of STD, which is our namespace, we're calling C out, essentially. Or we can use the namespace. So that's a lot of writing, if you think about it. Do we always want? How are we going to know this? And plus, every time we use C out, we have to go STD : C out, STD : C in. It's a lot of typing. So the using came around where we say using namespace, and then we can leave it out. So we put this in once, we leave it out in the code, and now we can just say C out and not using namespace. Because a lot of people, they fight the namespace for some reason. You know why? Because it never existed in C. And it came around in C++, and compilers just started using it. Like Dev C++, Microsoft, Visual C++. All of a sudden, this using namespace came out. Well, where did that come from? We never used to that before. And it was only because, well, third-party libraries became very popular. And you think of the concept, the more library usage you have, it became a problem. And then it avoided a lot of mistakes, avoided a lot of errors with the compiler. Nothing more than a compiler-related thing. It has nothing to do with the source code. Your source code is identical with or without it. Only problem is now you have the the ability to load in a ton of libraries from third-party sources, and you don't have to go back to this list here. You don't have to ask them to, you don't have to recompile it. You don't have to ask them to change something or not use it. You can use them all, and you can essentially include anything you want in terms of that code. So we use the using namespace, and the terminology just says using namespace, and then we can just say using namespace again if we want. So here we have a different one. So here's how you define your own namespace, and you can do this. So here we have include IOStream namespace. My names looks like a function. Normally you would say integer or void main, or you said, but we don't have. It's not a function because we don't have the opening and closing brackets here. We're not taking on parameters. We're just saying namespace my names. Inside I have integer value 1 is equal to 10, integer value 2 is equal to 20. And I have a function in here, compute sum, and the compute sum is going to return the values of the two added together. And then out here in main, I've got std, because I didn't say including out here. I didn't include it. I just created this namespace my names. It's kind of like creating a function and then calling the function, but here we're just saying inside of my names run compute sum. And then, from std, : run the end line. So if you came in a little late, what we're looking at is instead of doing this without using the namespace with the scope resolution operator, we start using the scope resolution operator here because we're not using namespace anything. If we wanted to, we could say using namespace std, using namespace my names, and we could solve the problem. I mean, we could not really solve the problem, but what we're doing is using namespace standard, using namespace my names, using namespace my other names. So what we're looking at are, draw a line down the center. Here's one set of source code, here's another set of source code. And here, this is our main. And we didn't say anything about, we haven't said integer value 1 is equal to anything. All we're doing now is we're calling value 1 and we're saying value 1 is equal to 50. I'm like, well, where did value 1 come from? Well, it's in one of these namespaces. When we go back over here, we say namespace my names, well, value 1 is 10, value 2 is 20. Namespace my other names, we're ambiguous. So if you use multiple namespace statements, you may get a compiler error due to the ambiguity that exists as well. So Although this was put in as a solution to environment variables and to conflicts with duplicate identifier names, as we see in this particular example, it can cause ambiguity as well. Here, how do you know, because you got my names and my other names included, which value 1 are we actually setting? And we're going to get the same compiler error than if we didn't include a namespace at all. And we had all these libraries in there, and one of them's got there's 2 of the same identifier in there. And I would say that that's probably one of the most difficult parts of C++ programming when using third-party libraries, is fixing the compiler errors. There's nothing wrong with your code. It's just that, in both of the libraries that you're using, the same variables are being defined, or the same functions are being defined. And so the compiler is going to be upset. And what ends up happening is a lot of inexperienced programmers, they go through, they start changing stuff around to fix the problem. And then they realize, well, the problem's not associated with me, it's associated with these libraries. And then they figure out, oh, namespaces, let's try that. And that's usually the better fix, is what it is. So you can also define nested namespaces as well. So you can put a namespace inside of a namespace. So here we've seen the syntax. It looks like a function, just to reiterate the point. Namespace, namespace, my other namespace. It looks like a function, but it really isn't. You're defining a namespace because you're using the word namespace here. We've got these, yes?
Is it like initializing the values?
It is. In the namespace, you could put functions. You came in before this. You missed this part. You could put variables, you could put functions, you could put all sorts of different things in there.
But for the values which are declared in the namespace, do they have any scope? I mean, private?
The namespace itself gives us the environment space, the block. It gives us the scope. And so we put things in the namespace. We could declare variables, we could declare functions, we could do anything we want in this namespace. And all we're doing is setting an environment scope so that we have access to use this information. If, for example, you included a library called myprinter.com, myprinter.h. In myprinter.h, there's a function that we're going to call. Actually, let's just talk about iostream.h. We already know a couple of them, C in and C outs. If we had another library, my iostream.h, and it also had a C in and a C out, and we used it, the compiler would come back and say, which C in and C out are you talking about? Because we included 2 libraries with the same names, same identifier. So when we have duplicate identifiers, the compiler chokes. So what we would normally do is create 2 different namespaces, put one of them in each one, and say, using namespace this, using namespace that. Or we take this approach here and we go from std : use C out. And then we can go std1 : C out. So we can use the same name in the same program, but we have different environment spaces. So the namespace came around with C++, as I mentioned earlier, because third-party libraries, very important, which, kind of different than the Java concept. Java packages, I want to say, are a little bit more organized than third-party libraries in C++. And we don't have this concept in Java, actually, because we have the JVM who's managing everything for us. We have no JVM here. We're working with a runtime compiler of the operating system. So namespaces is one of those features that was added with C++ to give us some more flexibility to solve some compiler error issues. And you can program forever without even knowing what it's all about. In fact, if you're just writing one file and you're compiling it, then you may never even run into a case. The only thing is, like when you open up a project and you create a C file, the compiler itself might complain, what namespace are you talking about? You're forgetting about my namespace. Where's my namespace? Because a lot of compilers are now configured by default to look for a namespace. So if you leave it out, you might get an error. So people just put it in, and what they're going to put in is using namespace std. You'll see that if you just create a file, create a blanket, a blank project in Dev C++ or in Microsoft Visual C++. All right, so we have our ambiguity that's going on. We can also define nested namespaces, as we've seen here, with the namespace my names. Inside of my names, we have a namespace my inner names. Just as if you needed more. We have value 3 is in there. And then out here we have called them literally my names, scope resolution operator, my inner names, scope resolution operator value 3.
Does this come, my inner names, does that come under like a child?
Yep, it's a child because it's nested inside. My inner names is inside of my names. It's defined in there. So what I'm doing is kind of twofold. I'm explaining namespaces and I'm also explaining the scope resolution operator, which is different. It's brand new to C++, does not exist in Java. You cannot do this. The scope resolution operator are the two colons that look like a square. You use this to resolve the scope. As an example, inside of std namespace, we have cout. Inside of my names up here, we have value 1. Inside of my names, my inner names, we have value 3.
Can we write value 2 there, Professor?
If we wrote value 2, it would come out with an error message because it doesn't exist.
Because we are, it's also inside my names, right?
No, this my inner names only has value 3, so if I said my inner names here and I put value 2 here instead of value 3, you wouldn't know about it. I'd have to go back and use it like this. I'd have to say my names value 2. This is only going to know, this is basically, think of it sort of like a tree. It's traversing in, so you're changing the scope. When I do this with the scope resolution operator, I'm saying inside of my names, take me to my inner names, and inside of my inner names, give me value 3. And if it goes inside of my inner names and says, give me value 2, it's going to say not found. They give it a dictionary lookup if you want to. And we're traversing the tree in terms of the scope. That's the hardest thing for C++ people to comprehend, because what ends up happening is we build an interface to a class, or we build a class template, and then we say, implement this method. And then you start having to use the scope resolution operator, and they go, oh, because inside of this class we have a method. Inside of this class we have this method that's inside of this method. You know, and you have to figure out where you're going, because if you want to overwrite it, you want to change the behavior of it. So you use this, and we're going to see it later with methods and writing method bodies for a class. We're going to have to use the scope resolution operator. Completely different than Java. Yes?
Can you include the namespaces outside of this file?
Yes, you may. You can, in this particular example, outside of this file here, this could be in a different file, we can include this file. And then in the other file, we can say using namespace standard. As an example, this one's built in. We're just saying using namespace. Somewhere out in the compiler files, there's a file. And what it's actually called namespace something, namespace.h or something. We don't actually have to include it. It's included by default. But we're already, that's a standard namespace. It's already defined for us, and we're just using it. So what a lot of people, and that brings up an excellent point, a lot of people have namespace files. And then they just say, hey, using this namespace standard. And like, well, where was that defined in this program? Here's our total this is our total hello world program. Where is that namespace defined? It's not. It could be using namespace my names. So it could be anywhere. That's one of the beauty of C++, actually. You can divide things out into separate files, header files, and include the header files, or not include the header files. In terms of the namespaces, a lot of the compiler tools have properties and menu items where you can create namespaces as well. So it's usually part of the IDE, and it can also be done manually in terms of setting it. In this particular example, this could all be one file. This could be broken down into 2 files. You include one into the other. So it depends on how you want to configure it, essentially. Oops. Yes?
How the program calls it, like where do we save that another function?
Depends on your compiler. Dev does it different than C++. Most people don't create namespaces until they have a problem. Seriously. And when they have a problem, they'll do it inside of one of their header files. That'll be part of the package, or project is what I want to say. So they'll include a header file in the project that'll define the namespaces. And the namespaces will do nothing more than include a .h file. So you can take a namespace and then just include header files in it. If you're doing that, you're including all the libraries. So if I had 2 IO streams, my IO stream and IO stream, create 2 namespaces. Use this one, use that one, use this one, use that one. And then I can tell which one it wants to use. So in the old days, we couldn't tell it to use this one, use that one. We just couldn't use them. We had to rename them or something, or recompile the libraries, or ask the manufacturer of the library to change it. They're not going to do that. So. Very good questions. Are there any more on namespaces? Better to ask now than, because this is the last I'm actually going to talk about it. Yeah?
What will happen in the main program? We are not saying my names, which includes my inner names. We just say my inner names.
Uh-huh. Well, in this particular case, we're not using the including, or using namespace anything. We did it manually. If we wanted to, we can just include, we could have said using namespace my names, and inside, because we're using my names, inside we would already have my inner name, so we wouldn't have to call that either. We could use the outer and we get everything inside of it too. Which is one of the reasons why people nest.
Is it the inheritance?
Yep.
Then if we call just my names, we can
No,
get the
excuse
value
me. That's not what I meant. I mean, no to your question.
Okay.
I answered a different question than you said.
Okay.
No, there's no inheritance.
Okay.
So
Actually,
my inner names does not inherit anything. The interesting thing about C++ is that the scope rules are within the block structure. Anytime you have an opening and a closing block, you have limited scope, which is why in a function, what happens in a function stays in a function. And we'll see later that what ends up happening in that particular case is that we have call by value and call by reference that we have to do in terms of the function call, which we don't have in Java. So slightly different. Same concept though with blocks. In Java, you have block. What's in a block is in a block. So, but the scope is slightly different in terms of how it's implemented. Any other really good questions about namespaces? Hear a lot of chitter chatter. Yeah?
When calling in a function, when it's kind of calling in a function, right? I mean, function inside a function. So what is the main purpose of...
You can't actually put a function inside of a function.
Oh yeah, I mean, but you can call a function which is also...
You can call a function, yes.
It's almost kind of that, like...
Yeah.
So,
Yeah, you could have easily put this in two separate namespaces.
what is it?
It's just telling you that you can, if you want. I don't know if there was ever a case. In fact, personally, as long as I've been, well, I've done it maybe twice. I've created namespaces. And that was a case in which I was using drivers from
Is there any specific
header
use for-
files. Huh?
Is there any specific use for this?
Yeah, for drivers. like I was trying to say, in the course of the entire history of my programming with C++, I've used it maybe twice. And I've been doing this for years. And I've only had to do it twice. And I've only done it because I've had to. And in that particular case, it was because I was using drivers. One was for a scanning program that was using a driver that was from a manufacturer that redefined, where he was using the same identifier names as another scanner device, and I wanted the program to work with both scanners. And in order to do that, I had to create two different namespaces and says, hey, using HP, using Xerox, you know, and switch back and forth between the two of them in order to. Everyone's going to say, you know, everything's a write, everything's a read. You know, if you think about the concept of people who write drivers, they're always using generic open, close, read, write. All these calls are like the same names. And if you include this driver and you're saying write, it's like, okay, are you talking about write from this driver or write from that driver? Yeah, it has problems. And it's just the compiler having problems resolving the name. And there's a conflict because there's two of them in the same space. So, yeah, that's the only reason why you create a namespace, really. Why compilers have made this the default, I don't know. It's only been in the last several years, I'd say maybe last 5 years or so, that dev C++, now we have using namespace standard on the template. So there's a lot of chitter chatter in the back. Are you talking on the phone? Oh, could you take that outside because it's distracting me, I'm sorry. Yeah, thank you. I can hear you. Way up here. Alright, so any more questions on namespaces? Those are very good questions. In fact, this is how we generate some good discussion actually on it. Let's move on. Numeric data types. I talked about this before. What I'm trying to do is allude to the concept of what data really is in terms of a variable and how we're using the variable. What we've got essentially is a type character that represents individual characters and small integers or 1 byte. So what I'm going to do is kind of ease you into data types, talk about variables, and then I'm going to hit pointers. So this makes it kind of baby steps into the process because pointers are nothing more than variables. But you have to really understand what a variable actually is outside of just taking it for granted, integer I. There's some people, believe it or not, that just make all variables the same data type. And the data type itself is so varied depending upon language, the language that you're using. And some C++ compilers have different sets of data types than other C++ compilers, which makes them a little bit different. So it depends on what the compiler supports, longs, shorts, wides, narrows, in terms of the length and how much memory can be stored, how many words. So types are usually character represented by bytes. And so types short, integer, and long represents integer values, half machine word, one machine word, or one or more machine words. So what we get is this unit of measurement. And when we say integer I, we get, I don't know, maybe 2 words, 3 words. And it's represented in terms of integer. In fact, the space is allocated in whole integer values normally that equate to bytes. There's some equation at the end that says, when I say integer I, the compiler goes out into my available memory resources for the process that I'm running in and says, give me 1, give me 2, depending upon what I asked for, bytes. And then it gets, the word identifier comes out of this. And these are called named variables because I am associating it with an identifier that I'm calling I. So I said integer I. So I'm referring to that space as I. That's what everybody's comfortable with because that's the same in any other programming language. That's variables. That's what we're familiar with data types, whether we use them correctly or not, because we have to give each variable a data type. Otherwise we get an error message. So types of float, double, long represent floating point values, 1 word, 2 words, 3 words, 4. Characters, in terms of characters, short, integer, long, also called integral types. They can be signed or unsigned. And that kind of begs the question, well, what are we really talking about? So in C++, we have this concept of type, and then we have user-defined types. And when we start creating user-defined types, we start saying, well, what is the allowable range of values for the type? And the second component of it is, what are the operations that we can perform on this type? And that's the basic concept of the abstract data type as it's implemented in C++. Same concept as in Java. The only thing is you actually have a little bit more control because we have a wider range of data type capabilities depending upon the language. So in C++, we have this thing called a structure, that I'm going to talk about today. This thing called a union, that I'm going to talk about. This thing called an enumeration type. We also have type defines, and we also have classes. So most people equate C++ with the class, which is the object-oriented term used on the abstract data type, the only abstract data type that you can actually create. It's truly C++. Prior to the class, we had unions and structures. So the interesting thing about using C++ as an object-oriented data type, object-oriented programming language, is you got, what did I just mention? Structures, unions, enumerations, type defines, classes. That's 5 right there. What do you got in Java? 1. Class. You create a class. Everything's a class. Nothing else. No other choices. So the 5 different, what I just spilled off of those 5 little off, it makes it more complicated for people to conceptualize at first, which is why a lot of people think that C++ is harder than Java. Well, because you got 5 more options. It's harder, but you got a lot more, there's a lot more functionality. And we'll see that the structure and the union are very similar. So once you know what a structure is, you can create a union, no problem. And I'll talk about that in a few minutes. Enumeration types aren't supported at all in Java, and neither are pointers. Another topic. So what I'm going to do today is throw out all these topics to you, or as much as I can get through, and then continue next week with the rest of them. And then we're going to hit each one of them in a lot more detail, so you can actually see how it works in an object-oriented fashion, which is kind of the way that after boot camp, or first lecture after boot camp, is kind of the course that we're following over the next couple of weeks. But I'd like to give you all the options first, so at least you know the big picture to see what we're going to. Alright, so going back to the concept of the numeric data type, the built-in data types work the same way as the abstract data types, or the ADTs. And they call them abstract data type because they're user-defined. That's the only difference. So in the built-in data types, in the numeric concept, we either have signed or unsigned values that are associated with it, which means it's plus or minus the 0 point on the axis. Or we also have arrangeable values. Arrangeable values are determined by the types. The type says for an integer there's 2 byte spaces, which means we can only store a value that's going to fit in 2 byte spaces or something. I don't know actually how many there are for that, but. And then we have this concept of named memory storage, which is really the variable. So you can write to it, read from it, manipulate from it, and you access the memory by the variable name. And I know a lot of you guys know this stuff already, but you have to really think about what you're actually, because a lot of people just take it for granted. But when I say integer I, I'm actually reserving memory space. I'm accessing I, I'm using I through this, and the term is a named memory. So sometimes it's referred to as named memory, because you're not accessing it from the memory address or from a pointer to the memory address. It's from the identifier, which is what I say. You declare and then you initialize. When you declare a variable, you've given it an identifier. I'm declaring a variable integer. Well, it's storing an integer value, and I'm giving it the identifier I. And then I initialize it by saying I is equal to 1. Otherwise, your variable is not initialized. There are some languages that actually, by default, initialize everything to 0, or everything to a space. But if I were to do this and I were making a mistake, and I said print out I, and I didn't initialize it to anything, I'm going to get whatever is at that memory location, the last time that memory location was used. Sometimes it's empty, sometimes it's a 0, sometimes it's those really weird characters that show up on the screen, and I'm sure we've all done it in some language. So each variable has a specific type associated with it that determines the size of the layout associated with memory, the range of values that can be stored, and the set of operations that can be applied to it. Variables are often referred to as objects. So C++ took the variable, turned it into an object, actually. Because what is an object? It's the implementation, well, it's implemented by a class. What's a class? It has an allowable range of values that are associated with it, the data types, and it has allowable operations that you can perform on it. It's essentially the same thing by definition. So people started calling variables objects, essentially. So 2 different variables associated, values associated with a variable. The values are on the left and the right. This you guys already know. This is programming 101. We covered this in boot camp. We had the data value. The data value is associated with some memory. That's a memory address. It's referred to as the R value or the read value. This is the definition of these terms you probably learned a long time ago. And then we have the L value, the location value. So the read value is the data value. And then we have the address value. The address value nobody looks at until they start looking at pointers. Then you realize we have an R value and we have an L value. The read value is when you say, what is I? Well, in the last line of code I said I is equal to 1, so I guess it's 1. The L value says I is hash 954782 whatever, some ASCII number that I don't recognize because we don't really know. We don't actually care what address it's at. But it's address indicating the memory location where the value is actually stored in memory. So the value is also referred to as the L value or location value. So let's talk about pointers. Not too bad. Easy. I don't know why students don't like them. It's the same thing. We've been talking about pointers already.
I've heard of pointers.
Have you heard of pointers? You've never heard of pointers?
No, everybody's afraid of pointers.
Everybody's afraid of pointers. Why? We've been talking about them already. They're nothing more than variables. What do we have here? We have a name. What do we call the name? It's an integer I. So we don't have the I. But we still have the L value, and we go to the L value and retrieve the value that I is equal to. Naturally, when we say use I, print out I. So let's talk about pointers. It's the same thing. Just keep that in the back of your head. Pointer holds the memory address of another object. So through the pointer, we can directly manipulate the referenced object. So this was called named memory storage, because we put I as a label, or my variable as a label to that memory address. This is unnamed, or it's referred to as referenced objects. We can't do this in Java. So and this is what confuses everybody with C++. Pointers are useful. Why do we even want to do this? Well, for creating data structures that we can do manually in C++ that we can't do in Java. Well, actually, we have built-in libraries for it, but makes it easier. That's what makes Java an easier programming language, actually. There's a lot more built-in functionality. We can create linked data structures such as trees and lists. We'll look at the linked list. We'll create a linked list in the weeks to come. We can manage dynamically allocated objects and as a function parameter type for passing large objects such as arrays. I'm going to save arrays until I get done talking about pointers because an array is a pointer implementation of a named variable. So why would we want to talk to the memory address directly? What if we have a huge memory address? Here's the two scenarios. We don't want to use pointers, we're afraid of pointers, don't want to use them. So instead, we don't even want to use arrays. Instead we got integer A, integer B, integer C. How many letters? We got 26 characters. We got all of that entire alphabet is used up. And we got all these different variables. And they got 1, 2, 3, we got all these different values. We got to keep track of a lot of different named variables by name. And we got to constantly copy this one to this one, this one to this one, this one. There's a lot of juggling, a lot of copying, a lot of memory that's wasted. We've now used 26 memory locations. If we just used one memory location and created a pointer, we could have everything point. All 26 of those characters can point to that one memory address. Now we're only using one piece of memory instead of 26 pieces of memory. And we're still juggling through A through Z. Which is why it conserves memory, makes it efficient. And let's talk about parameters for functions. We talked about functions during the boot camp. You should know what that is by now, hopefully, even if you're brand new. We send a value to a function. It's a lot of memory we're sending. If we send it by value, we say send I. What if we say A through Z to the function? That's a lot. Why don't we just send the memory address of all of this crap? This one memory location. And we actually send the address, we don't send the data. So we don't carry the weight of all of the data and the size of that data. We're not sending any of that. We're just sending, hey, here's the reference to that particular memory address. Inside of the function, go out to that memory address so you can get what you're looking for. What we're doing. And in a function where we're doing that, we can change it permanently. So in a function we talked about during the boot camp, passed by value, what happens in Vegas stays in Vegas. In the function, you send I to the function. You're sending a copy of I, which is a value that's associated with I, because we said I is equal to 1, let's say. So send I to the function. And inside of the function, I gets added to another I equals 2 now. Unless we return it back out, it stays in the function. Whatever happens, whatever changes to I, changes, we don't care about. It happened to the function, stays in the function. Happens in Vegas, stays in Vegas. If we want it, we have to return it back out. We have to take it home with us, bring it back out into main. So we got copy in, copy out, waste memory. Every time you do that, you're using up more memory to send something to a function, to return something from a function. Which is why you don't want to return something from a function unless you're actually going to use it, because it's a waste. When you use references, you're not sending anything. It's kind of like, here's my address. Send me an email if you want. Okay. I haven't wasted any internet time. I haven't done anything. I just have the address if I want to use it. If I want to use it inside the function, I go out to the address, I change it. I add something to that memory address, I change it. I don't have to pass anything back out of the function. When I end the function, whatever got changed in that memory location is still changed. And so everything's permanent. So we have different rules on when I talk about how arrays are implemented. We'll see how that's different from other variables, but I'll save that discussion for another outside of the orientation to functions, to pointers. But so yeah, for sending large objects, don't send the large object, just send a reference to the large object. Say, hey, it's over here. If you want it, it's over here. Use it over here. Oh, okay. And it's very not as time consuming as sending the entire object. It's kind of like if you're moving. So you pack up all your stuff, put it in boxes, and take it with you. Or when you get there, you can send a moving truck out and go get your stuff. You're traveling with a lot less of a load with you. So it's you can get there faster, hopefully. Use less gas in your car. Maybe that's a bad example, who knows. All right, so every pointer has an associated type. So every pointer is nothing more than a variable, but instead of putting a name on it, we're just using the address. It still has to have a type. We still have to know what we're going to store there. So if we're going to use an integer, we're going to store an integer in this pointer, then we have to create the integer pointer and a double pointer or a float pointer. Same types associated with regular old variables. So the type of the pointer tells the compiler how to interpret the memory contents at the reference location. Think of it sort of like a format. Now, it's like we're going to create an integer pointer. It's going to hold an integer. And how many bytes this interpretation includes. So, as an example, here's some formal pointer definitions. And here's where things get tricky. Because for some reason in C++, the reference and the dereference are the same character. And this messes everybody up. Right now we haven't seen dereferencing yet, but what we're doing right now is referencing. And we use this asterisk as a reference. So some people like to put a space in here, and they go integer space asterisk space pointer, and pointer is the name. You can think of this as integer I if you want. We're calling this variable pointer. Or some people like to go integer asterisk space pointer. The asterisk has to show up somewhere in between these two things, and there has to be a space between the data type and the name. If I said integer I say I-N-I-T-T, or let's call it, no, integer, that's T-T, that's integer T. Integer I-N-I-T-I, and I didn't put a space in there, I get an error message because I'm calling my variable I. There has to be a space between the data type and the name of the variable that you're declaring, just by standard convention. Where this asterisk appears doesn't matter, but when I say integer pointer with this asterisk, now I say I'm creating a variable, same as before. So if I pulled this out, I'd still be looking at the same thing. This is the only new part. I can do it this way as well. If I said integer I, comma, t, I can do them in a line. I can use string. This is the integer so far. I can make it a string, I can make it a double, I can make it a float. Any data type you want, you declare the value of that particular integer. Or, excuse me, variable. So I mentioned this reference and this dereference. This says we're going to create, let's just look at the top line here. We're going to create a variable and we're going to call it pointer. If I leave this out, I said integer pointer. And I would say pointer is equal to 1. And I would assign this value to 1, which is a valid pointer, which is a valid integer number that I can assign to an integer variable. Because I put this asterisk in, it says, okay, give me a memory address of size integer. And we're going to call it out here, we're going to call it pointer. And if I said pointer is equal to 1, the pointer is actually looking for a memory address. So I would give it the memory address of 1, not the value of 1. So when I do this, when I declare variables of pointer type, I need to initialize it with a memory address, not a value, because I want pointer 1 to be a memory address. I'm doing this out, this doesn't take up any memory, actually. It doesn't take up any memory until I assign it a memory address. I haven't actually created a memory address yet. So this is when we're going to end up with new and delete, which is how we dynamically allocate memory. And I'm not going to talk about that today, I'm just going to introduce pointers today. We can create our own memory. We say new integer, and then I can say pointer is equal to the address of this new integer. And we go, whoa. It's like, so I'm no longer creating identifiers, instead I'm creating pointer variables and I'm having them point to memory addresses. The only difference, that's the only difference between variables and pointers. So we have the dereference operator. The dereferences a pointer variable so that you can manipulate the memory content at that particular reference. So here we're using the asterisk as a reference. We're saying, give me a reference variable, call it pointer. If I said asterisk pointer equals a memory address, I'm assigning it, I'm dereferencing, I'm following the pointer. So referencing means give me a reference to a memory address. Dereferencing means follow this variable and give me what's at the memory address that's stored by this pointer. Not going to understand, if this is brand new to you, it's going to take not till the next lecture, till this is really clear. You sort of have to blindly accept some of these terminologies and then we'll see it working. So the dereference, a pointer to the variable that can be manipulated to manipulate the memory content that the pointer is actually pointing to. And then we have this thing called the ampersand, or the address of operator. So the address of operator provides the memory address a pointer is actually given. So of any particular pointer, we can say, give me the address. So if I said in here, leave out the integer, I said ampersand pointer, I'm going to get the memory address of that particular pointer and not what's at that pointer. Alright, so let's take a look here for a few minutes. Correct or incorrect? Let's see. And this is just looking at referencing and dereferencing and the address of the three operators that we've looked at so far. We have, forget pointers completely. We have integer variable 1, regular variable that we've seen before, is equal to 333. And then we have variable 2 that's equal to 444. And then the same thing, but now we've used this asterisk, which says we're not going to create a variable, instead we're going to create a pointer. No, it's a pointer variable. It's the same thing. It is a variable, but it's a pointer type variable. And we have pointer variable 1, pointer variable 2. This is a legal syntax. This is legal syntax. You can do this. You declare pointer variables the same way as you declare regular variables. Let's do some operations. We can't say that pointer variable 1 is equal to variable 1, which would be incorrect because we have mismatched data types. As I mentioned before, C++ is very type conscious. Strict, I should say. We can't mix and match types. So we can never have these two equal. This is like saying, integer A, integer B. A is equal to B. That would work just fine. They're both integers. But if one's a pointer and one's an integer, well, the pointer doesn't want a value. It wants a memory address assigned to it. It's not going to work. It's going to be incompatible. But if we said pointer variable 2, it's a pointer, okay, equals the memory address of variable 2, that works because we're assigning a pointer to a pointer. Because we've got this pointer wants a memory address, it doesn't want a value. The only difference between a pointer and a regular variable is the pointer wants the memory address. Because it's not going to use the value. The value is at the memory address. You're saying, okay, which memory address do you want me to reference? You give it a memory address and you can put whatever you want at the memory address. And the ampersand operator here, you can just say the value at, if you want to substitute when you read this, the value at variable 2. The reference, the address of variable 2 is probably a better way of saying it. So the address of variable 2, that's an address. Okay, so follow. In any other case, this would be a reference. This is a dereference. We say follow, so you can substitute, when you're dereferencing, you can substitute the asterisk for the word follow. Follow P variable 1. It's going to the memory address now. Have it equal to variable 2. Well, variable 2 is a value because value is equal to 444. So now the memory address of P value variable 1 is now equal to 444, which works. This is what confuses everybody because this is a reference and this is a dereference. This reference a memory space, follow the memory space, have it equal to variable 2. And it's going to be equal to 444 because that's what variable 2 is equal to. And then better yet, follow variable 2, have it equal to follow variable 1 plus 100. Well, if I followed variable 1 What's variable 1? It's not equal to anything. Oh, plus going to be equal to 100. Now is when I start getting the blank stares.
If you
Yeah.
don't,
Yes?
if you don't initialize, it's like whenever we are initializing, like it's.
This would be the
pointer of
initialization, huh?
Yeah, in initialization we have declared as pointer of.
If we're going to initialize it as a pointer, excuse me, if we're going to declare it as a
Okay,
pointer,
yeah,
we
we
initialize
declare
it with a
actually,
memory address.
sorry,
Yeah.
We didn't declare initially.
Yeah.
And if we want to declare here directly, it's like we can write pointer of pointer p variable of one. We can dereference here. Directly.
We can dereference for an assignment. We've done it right here, actually. We've taken a memory address. Actually, here we've done it. We've dereferenced this. We said follow pointer variable 1, have it equal to variable 2. So the result of this is that whatever is at this memory address here is going to be equal to 444. I'm not quite sure if I understood your question. If you can try it again, maybe? Or does somebody else understand it? Yeah.
We didn't declare that actually. P variable, pointer of p variable.
We did. This is the declaration statement.
Yeah,
And these
for
are
example,
initializations.
actually, here
Okay,
we
hypothetically, if this wasn't...
We declare only int variable 1 equals to 333. And
Okay.
We declared only variable 1 in variable
Okay,
2.
perfect. Yeah.
And here we declare int. Here we declare int of pointer of pointer p variable 1 equals to something. Variable 2.
We can assign it anything as we want to assign it to, as long as it's a value. We could say the number 2, yeah. We don't have to say, we could say this is equal to 5. We could substitute the values of any variable with a number.
Pointer of pointer variable p of. Can we use 2 pointers like?
Oh yeah, definitely. You can assign one pointer memory address to another pointer memory address. You can say follow this one and have it equal to that one. Or you could say, because what you can do, you're storing a memory address. So the variable, as long as you remember, and you almost just have to memorize this, the variable is actually storing a memory address, not a value. That's the only thing different. A pointer is a variable that stores a memory address. A non-pointer stores a value. So if I had integer I and I had I is equal to 5, that's a variable. We're all familiar and comfortable with that, storing a value of 5. If I said, give me integer pointer, I use that asterisk, I. And if I said I is equal to 5, it's going to come back with, oh, an error message. Unless 5 is a valid memory address on the system. Instead, I could say, give me the, I have another variable f that or x, variable x, integer 5. Excuse me, integer x, pointer, integer I, follow I, dereference I with an asterisk, is equal to the address of x. Both variables would be pointing to the same memory address. So if I changed x, it would also change I. And we'll see that later on. Don't worry about it at this point. I'm giving you the differences between referenced memory and named memory. This is not your full pointer lecture. This is your orientation to the concept. I feel that if I don't orient you first, when you start learning it, it can be a bit overwhelming. So
we can declare int of pointer some p variable.
Oh yeah, you can take one pointer and have it equal to another pointer. You can take one pointer, have it equal to another pointer plus another pointer. You use them the same way. Anything that's valid on a named variable, you can do on a pointer variable. As long as you're always assigning the pointer variable the address of something. Has to be a memory address. Only difference, pointers store memory addresses, variables store values. You can think of the ease of use. Isn't it easier to keep track of values? I want to say integer I. Named variable I is equal to 5. A lot easier than saying go to the address of I, have it equal to 5. So it's automation. Named variables give you a lot more automation. This is just taking away some of the automation and saying, well, at this memory address, put the number 5. You can do the same operations on both, except for you don't have to pass 5 back and forth. You're not passing the data, you're just passing a memory address. Just saying, go to this memory address when I want to use it. Notice that in the pointer definition, the asterisk symbol indicates the pointer type, and it is not the dereferenced In this particular case, it's called a reference. If you can get the concept of what the pointer is by definition, you'll be successful. Don't worry about knowing exactly how to use them. I have a full, entire 2 weeks or so of pointer lectures coming up. This is the baby steps. Okay. So here's an example. We have integer variable, integer, follow p-value 1, have it equal to variable. So it's not a dereference in here. We've got, this is not, excuse me, this is a I said that totally wrong. Scratch what I just said. This is a reference, not a dereference. I'm going down here already. So this is, I'm saying integer, this reference to this particular variable is equal to variable. What is variable at this point is garbage, actually. It's garbage at some location out there. So it's incorrect. So during the initialization, a pointer can only be assigned an address. So we say integer variable, and the correct way of saying it would be the address of variable. If we say this, let's say variable, integer variable, the next line underneath, let's change this and say maybe this said integer variable is equal to 5. And then we said integer reference, give me a pointer variable, call it p variable 1. And if we said equals to variable, would it be equal to 5? Do we have a memory location out there called 5 that we've referenced? Probably not. Referencing, we don't actually get the addresses either. We never have to worry about keeping track of addresses. The C++ variable concept does it for us. The pointer actually manages the addresses for us. It already finds an available address that's in the memory management system and puts a label on it. It's kind of the same concept of creating a variable. We're labeling memory addresses, but now we're labeling them as addresses instead of as variables. So in here, if we said 5, it may not be a valid memory location. We haven't assigned it an address, we've assigned it the value of a variable, which makes no sense. So there's no meaning in this right here. If we say the address of variable, what have we done? Now we have integer variable and we have this pointer, and they're both pointing to the same memory location. Which means if we change variable, it's going to change whatever p variable 1 is pointing to, which is the same address. So now we have two variables that are both using the same memory address. Another reason why pointers are efficient, because you're only using one memory address. And now we have to, well, what about going back to my example of the alphabet? We can have 26 variables all pointing to the same memory location. So if something happens with one of those numbers, it's going to change it for everybody. So now we have shared memory. That's how we share memory. We have multiple variables all pointing to the same memory address. So if you can think of the concept of this, this is how we come up with linked lists, how we come up with these complex data structures, how we can manipulate memory through multiple different references to it, more efficient than copying it around all over the place. So, which is why C has actually got some power to it compared to some other languages, which is why it's still very, very valuable out in the real world, because it's efficient. You can write something that's low level that actually manages the memory more efficiently in terms of the program. You can't do this in Java. So referencing is also referred to as aliasing. So it can be used as an alternative name for objects. So in most cases it's used as a formal parameter to a function. So we're referencing or aliasing a memory address that we're sending to a function that the function is going to manipulate. And reference type is determined by the following, by following the type of the specifier of the address of operator. So here we have integer, the address of reference value 1 is equal to value 1. So we say the address of this particular operator is equal to 333. If we substitute value 1 for the value of value 1 as in terms of the address of. I know the blank stares are starting already. Alright, so references, in terms of a reference, it must be initialized, otherwise it's garbage. If I say go out and reserve a memory space for me. Alright, I got it. If I say, well, what's at that space? Well, it's going to be garbage unless you initialize it. And in C++, it's not initialized by default. You'd think that they would have built that in, initialized all the zeros or something, but they didn't. Once defined, the reference cannot be made to reference to another object. So if you say the object type is an integer, it's an integer. And integers can't turn into floats or doubles or anything. Because if this is space that I've reserved as an integer, I've got one block, or 2 blocks, or whatever I said integers were valued at. And this is all language dependent. Each language will actually reserve different amounts of space. So if you're wondering why we have different C++ compilers, what's the difference between Dev C++ and Visual C++ and all these other ones out on the market? Aren't they all the same? Well, the definitions of the variables, the implementations of the variables, and the types are all different. Some of them are more efficient. Some of them are more reliable. Obviously, a language that overuses memory adds a little bit of a buffer between the spaces, doesn't allocate, sequentially or something. Might be more efficient, might be inefficient. So there's differences in that. All operations on the reference are actually applied to the object to which the reference refers to, which is why they call these objects. Because we have an object. Well, what's an object? It's an integer object. It's a float object. It's no longer a variable. It turns into a referenced object. And when we start creating classes, we see the class as an object. And we see that. And then we can start thinking about, well, where does the word object come from? It's generic. It's nothing more than reference to a memory location, which actually comes out of the pointer concept. Implemented in object-oriented design, people think, oh, it's something brand new. Well, object orientation actually did not start with C++, but it was heavily influenced upon reference to memory and the use of pointers in terms of the modern day implementation of object-oriented programming. But it actually did generate out of other languages that did use the pointer memory location concept versus variables. That's a totally different tangent. Okay, here's an example here of referencing. We have integer value 1 is equal to 333. The address of reference value 1 is equal to value 1 plus plus. Reference value 1 plus is equal to 100. So we're doing some manipulation. What's the result? Well, we can see it changed for both. Because we changed the value 1, we incremented 333, it turned into 334 in this line right here. But they're both, and this point is referring to the concept that they're both referring to the same memory location because we made one variable equal to the other one. So they're, the address of in terms of here is equal to
or value at address?
the address of. Whenever you see this ampersand, think of the address. Whenever you see the asterisk, it's either going to or it's referencing, coming from dereferencing or referencing. So, don't worry if you don't get it at this point. More to come. Gotta take this and... Okay, I talked about passing to functions already. So this is the second kind of look at this concept. Let's see exactly what's happening. As I mentioned before, pass by value. And believe it or not, Java is all pass by reference and everything is implemented in terms of reference and pointers. But the programmer never has to touch any of it. It's all done for you automatically. Everything in Java is pass by reference. We don't have pass by value. We can imagine it makes it more efficient. We're not copying stuff all over the place. Which, if we had our own JVM, yeah, sure, why not? We implement our own language. Alright, so the actual parameter cannot be changed by the function if only a copy of it's sent. This is like saying, hey, I got a birth certificate. Sure, let me give you a photocopy of it. Here's the photocopy. Do whatever you want with the photocopy. Destroy it, spill coffee on it. But my original birth certificate is still intact. Hasn't changed. Which is what you're doing when you send it to the function. It's like saying, make a photocopy of this letter and send it to somebody. Someone can burn it. It doesn't matter. I still have the original. So it sends a copy of the contents to the actual parameter. So the calling block would be like main, the function out here that's being called. I'm talking about the parameters that are sent to the function. This is why you have to know something about functions in order to understand what the parameters might be to a function. Pass by reference violates the Vegas rules. So you send the location or the memory address of the actual parameter to the function. I've sent you my real birth certificate. If you destroy it, it's as if I was never born. I have no documentation anymore. I've given you my passport. This is my passport. Ooh. Be very careful with it. Don't write all over it, you know. Treat it with care because I got to get it back from you. I get it back from you because I reference it again and I get whatever happened. Whatever you did to it, it's going to be permanent. Same thing happens in the pass by reference. So, because you're sending the memory address, you're not sending the variable. And multiple variables can point to the same memory address. So it can be changed inside of a function. It can also be changed inside of the same program. Whatever's pointing to that memory address, whatever you've given access to, it's like giving your password out. Whoever has your password can log into your system and do whatever they want. It affects you. It affects everybody else who has the same password, who's got the same access. Alright, let's look at the string type. So, in fact, that's our break in terms of the pointers. So what I wanted to do is compare references to variables. So you can kind of see the difference at this point. I got another 2 or 3 weeks of pointers coming up, but let's switch gears a little bit and talk about strings. In other languages like Java, we actually have this implemented as a primitive data type. We don't actually have this in C++. Instead, this is one of the things we get with C++ is the string.h library. And this is the most confusing thing. You're going to need this for your first or second, actually for your second assignment for this course, you're going to need to know about the string class. So we include string, and if you're not using dev, you've got a .h here. You remember that? So you use the C++ string type. So here's our first example of not a built-in primitive type. This is not a user-defined abstract data type either. This is a library type. This is very, very, very common. This is when we do all those includes. We're using types, we're using functions, we're using all sorts of stuff that was created for us that we just kind of not built into the basic language, but it's an add-on. So 6 different ways, different ways to initialize a string. We have string, my string, and the my string is going to be called hello folks. String my other string, which is equal to my string. Looks like a function call, sort of. Or string my final string, semicolon. This looks like a regular old variable type. Looks like a regular old integer double float. It's an empty string. And then we can say my final string is equal to something if we want to. And you can use the quotation marks to specify string without using a function call. This is more common. You'll see that a lot. So the length of the string is returned by the size operation without the terminating character. So we have here cout, which hopefully you're familiar with that already, my string.size. And this is equal to 12. Let's say it gets printed out, it's equal to 12 as an example. Because we have, I don't know, I didn't count all that stuff. But anyway, long story short, that's what it's going to be equal to. This is our first method call. And it's a method call because the string's actually an object. So when we do string my string, we have done the same. This is why, going back to what I said about variables being called objects in C++, we can run a method on an object in C++. We can't really do it in C because we don't have methods. We don't have classes in C. But if I said integer I, in C++ I can go I.size. And it's going to give me back the size of I, which is going to be, what did I say, 2 integer spaces or something? Whatever, byte spaces, whatever size is associated with a memory address that's created automatically when you declare a variable of type integer. So the method call says, well, we're going to run a method on an object whether it's an object or not. Well, in C++, believe it or not, everything is an object. Everything is an object. So we can say here, string, we've just created an object. We've done both. So if you remember that, it's kind of the same concept as Java, actually. So we can use the empty operation to find out whether or not the string is empty. So we can say boolean is string empty is equal to my string.empty. Come back true or false if it worked or not. So empty makes it empty. So you can use the equality operator to check whether 2 strings are equal. If my string is equal to my other string, is this object equal to the object? If it's 2 strings, it's going to come back and say, yeah, wow, the strings are equal. Are the strings really equal? Or are they both of the same object type? So you can copy one string to another with the assignment operator. My final string is equal to my other string. You can make them equal. So this is our, usually most C++ object-oriented courses start out with a string object because it's something you don't have to create, it's already given to you. And you can start running methods on it, you can start working with it. It kind of gives you your pre-exposure to you know, the concept of the object in a lot of different ways. You can use the plus operator to concatenate strings. So string S1 is equal to wow, string S2 is equal to ouch, and constant character pointer S3 is equal to yikes, yucks, and S2 is going to be equal to plus equal to. If you haven't figured this out, it's doing an assignment plus an addition at the same time. S1 plus S2 plus S3, and we got C out. S2 is going to say ouch, wow, yikes, ouch, or something of that nature. We concatenate them all together. If we use this operator, and this is the interesting thing, is this is overloaded in the string class. So the concept of overloading says if you're using a plus and it's 1 plus 1, we're going to have 2. If this is a string, we've overloaded it to say, well, and we've redefined the operator within the class. If you look at the body of string.h, you'll see that the plus symbol is overloaded to do concatenation instead of addition. So when we've done this, we've concatenated things together. So what you're doing in C++ when you create your own objects and your own classes is you're overloading operators, you're overloading functions, you're creating methods. A lot of the same stuff that you do with Java, actually, except for you have a little bit more, you have both systems running it simultaneously. Let me try to clarify that. In Java, you have only object orientation. And you only have objects, and everything's a class. In C++, you got that, plus you got everything that's not standard object orientation. So you can still do a structure, a type define, an enumeration. You can still have a function that's not part of a class. You can still have all sorts of different things that are going on. So you've got the best of both worlds, because you have both styles incorporated into one. And there are people that have programmed for years in C++ who have never done any object-oriented programming. But they think they have. Because they've been using C++, but they have never done anything object-oriented style. So object orientation is the methodology. It's the style of programming, given the tools. It's not the language that you're using. So let's take a look at the constant qualifier. We have this. Do we have this in Java? I don't think we have constant in Java. So going back to the concept of variables, we have literals, literal constants. When we say pi, constant double pi, this will be a literal constant actually. A constant type qualifier transforms an object into a constant. So we say, when is pi ever going to change? It's always going to be 3.1416. Most people just say 3.14. I don't know, 3.142 or something. You want to abbreviate it even further. Which means we've developed this, and we've used the keyword constant right in front of double. And now we've changed it into what's called a literal. It's a constant literal because it's never changes, we can't change. If we try to change it, the compiler comes back and says, hey, you can't change this. We can do this with methods inside of classes. Constant methods, we can do this with parameters. We can do all sorts of things to enforce rules to say, you can't override me. You can't change the definition of pi in this program or in this class. Which kind of gives you the ability to make it, enforce some integrity rules. So constants allow you to store parameters in well-defined places in your code. You can put them all up front. Have associated types. It must be initialized, of course, because if you can't change it, you got to assign it a value. Can't be modified after the declaration, and constants replace the define. So if anyone remembers the defines in C, that was replaced in C++ with the constant. You can still use define though, which is interesting. Because C and C++ are one and the same these days. But if you do the define, people think you're a C programmer. If you use constant, they go, oh, you're a C++ programmer. So, all right. Sometimes we want to also define your object as a set or a states of actions. So you can use the constant to say, as an example here, define the following states for student counselor. So observe student, shout at student, follow students, recharge batteries, I don't know. All these constant qualifiers. These are just variables you're creating to initiate some sort of a state or some sort of an action. And I'm leading to the concept of enumerations in a few minutes to give you a definition of that. An enumeration is nothing more than a bunch of constant characters, but they change. So using a constant qualifier, staying on this track, you can define the following constant states. Well, okay, so 1, 2, 3, and 4. If I were to say, well, what's number 3? Can't remember. Oh, it's follow the student. A lot easier to remember a name. It's kind of like why we put names on memory addresses, which is why some people find pointers more difficult, because there's no name that you can refer to that integer as. It's an address, and we don't even know the address. So we can put a name, a constant identifier, and we can kind of create our own variables that can't change that are meaning something. So a function, a set robot state, you could then be defined as following. Here we have set robot state is equal to an integer value, and these are all integers, new state. So we don't have to remember what 3 is, we can just say follow student. So robot state, follow the student. Okay, follow the student. So it's going to say, and inside we're going to say, you know, initialize current state is equal to new state. New state is what we sent to it. It was follow student, and follow student was equal to 3. We don't have to remember what 3 is. It's kind of like saying pick a color, red, white, or blue. One of them 0, 1, and 2. 3. You know, none of the above. I don't know. It's easy to remember colors. So that's where the enumeration type came from. That is a primitive enumeration. So C++ programmers were putting names on numbers to say, give me a value between 1 and 10. Is it high, low, or medium? So it would be 0, 1, 2. Well, I think it's a 2. Is that medium or high? And it makes more sense to put a name on it. So enumeration types are the same concept. Instead, you have integer values that are called names, like red, white, and blue. If you have an enumeration called colors, you could have red, white, and blue as part of your color mix. And red would be equal to 0, white would be 1, and blue would be 2. And those are the same concept. Basically, you have integer values. So mapping states into integers has this disadvantage here because you can't remember what you've got. If you organize it in terms of an enumeration, also does not exist in Java. We can remember it, so you can't retrain the range. In the manual way, without using enumeration types, you have no values, no ranges on the values. You just have a bunch of integers. It's like taking A through Z and applying it in 1 through 26. What about 27? You can put a 27 in there, no problem. Just create another variable, create another variable. They're all over the place. They're hard to organize. And there's no useful typing to it. So if you define individual sets of states with multiple objects, each object could formally be set to another object or state, not only to its individual state. So the problem is solved with enumerations. Let me give you an example of what this enumeration means. So we have enumeration types that are defined as, let's say, robot state. And robot state is equal to observed state, which is equal to 1, shout at student, follow student, recharge batteries. We call it, and this is our first user-defined type. And so now we're creating our own types. We can't do this in Java, because what kind of abstract data types do we have in Java? 1. We only have 1. It's a class. That's the only abstract data type we have in Java is a class. What do? We create classes. Hello World is a class. C++, how many did I name off earlier? 5 or so. We have more than just 5, but that I gave you today examples of about 5 of them. So this is the first example in terms of what we can do. And what we're saying is enumeration. Just like we could say structure, just like we could say type define, we use this key word here to say we're not creating an integer, we're not creating a float, a double, a constant. We're creating an enumeration. Enumeration is going to be called robo-state. Just the same way as we used the word namespace earlier. Actually, namespace is a type. It's an object that we can create as well outside of a class. So make that 6 instead of 5. So We have enumeration robostate. Robostate's got all the stuff in it. We have an opening and we have a closing bracket. This was the predecessor to the array, actually. Arrays are multiple of the same type. Enumerations are multiple of the same type, but they're all integers. So each one of the items in the enumeration equates to an integer value, and we're starting it out with 1. So if we said observe student is equal to 1, then shot at student is equal to 2, follow student is equal to 3, recharge batteries is equal to 4. And we've just created 1, 2, 3, 4 different integer values when we've encapsulated it into a complex data type, and we're calling it robostate. And the complex data type is an enumeration data type. So this way we define a new type, robostate, that can only assume 4 different values. So inside we've decided we can only have these 4 different values. And so these values are still correspond to integers. So we can say cout follow student gives you the output of 3. You print it out because we really have that same correspondence going on. But we're now able to retain the values, and we can pass the robostate to the 4 different legal state to 4 legal ones. So Boolean set robostate. We're using robostate as the data type now instead of integer, new state. So we can use it as a data type. We've created our new data type, and we've created a new type as an enumeration data type. So in C++, we create a lot of our own data types, abstract data types, that are nothing more than elaborate, complex types that define multiple different variables in the same type. We use the type because it helps us organize the data, which is essentially data types in a nutshell. Robostate current state is equal to new state, to return execution successful, another state. So an attempt to call robostate with an integer value or a value of a different enumeration type will cause an error at compile time. So now we can put a little control on it, and we can make it so that the compiler can type check, because we have a valid type now. So if we said integer I, float f, double d, and we said I is equal to d, the compiler can come back and say, hey, type mismatch. You can't do that. So if we said set robostate, robostate is our type now. We said robostate, this variable of robostate equals other variable of integer I. We have type mismatch. So we can enforce type checking. So by creating our formal types and going through the abstract data type kind of process, creating these user-defined types, we can let the compiler do our type checking. So we can have that added feature of the compiler working for us. You guys want to hear structures today, or you want to hear them next week? Some people are shaking their heads no. Some people are like, I give up. It's a good stopping point. So here's the roadmap of our data types. And let me talk about this slide for a few minutes. I won't go past this slide. This is a good stopping point. We're looking at different categories or branches, and this is the entire C++ language of data types. In the structured type, this is what we're referring to as the object-oriented realm, where we have arrays, structures, unions, and classes. Other languages just have classes, and they're stuck with a class. You can't create anything else. So we have a few other things in here. In terms of simple, they usually hold one value, or they hold multiple values of the same type. So simple, we just looked at the enumeration a few minutes ago. And trust me, that's not enough for you to start programming with enumerations. So it's just, I'm giving you, in fact, you don't have to do anything with enumerations in this class, because enumerations are sort of a thing of the past. They're not even supported in Java. But it's not bad to know what an enumeration is by definition. It is a simple string of integers, kind of the predecessor to the array. The array is a structured type. The reason why an array is a structured type is we have a one variable integer I. And we said, okay, let's make I an array of 10. Now we have 10 I's. Oh, and we have a structure that's created with that. And that's why it's referred to as a structured data type, because we have I0, I1, I2, I3. We have these index values where you can get at the values of each one of the 10 I's that's included in this array. Well, in the structured approach for a structure, We use a dot notation, same thing for a union, same thing for a class, actually. And they're just different types of structured, complex data types. And I say complex because they store more than one type. In the array we're stuck, though, which is kind of weird. It doesn't follow the same standard. If you have an array of integers, and we have 10 of them, all of them have to be integers. We can't put floats and doubles in with those integers, which is weird. In a structure, we can have integers, floats, doubles, everything else, and I'll talk about that next week. In union, we just have one of them. Unions and structures are pretty much the same thing, but we only have one choice in a union. Classes, we'll save that one for a couple weeks further down the road. It's the same as Java. So going back here, the integral by definition, this is our vocabulary lesson for today. Under the simple category, we have our integral, which are short, long. These are the built-in, sometimes referred to as built-in data types. Our simple or enumeration, not necessarily built-in. And then we have our floating points, which are part of simples. They're just nothing more than the float, the double, the long double, anything else that might be supported in the language. And obviously there's some missing here. We have characters. No, here's characters, but we don't have wide and short characters on this slide. We have, some things that are missing. And then we have this whole thing called address variables. That's where we have our pointers and our references. Looked at pointers today and the concept of referencing. Classes use referenced memory in some aspects because of the way it's dynamically allocated at runtime. When we reference memory, we don't know about it until it's actually created. So I'll talk about that a little bit later on in the course as well. But this is kind of our roadmap for where we're going next week. So next week I'll talk about structures and unions, and then the following week we'll get into classes. Questions from today? Again, don't worry, that was not your entire lecture on pointers. You're going to have a lot more coming up soon. Nope, okay, then we're done. Enjoy the rest of your afternoon and think about pointers.